let's talk about surface area. It's not like we didn't do surface area before. Why are we doing it again? Is the obvious question, isn't it? See, before we did this, our surface used to be this kind of surface, right? Quadratic surface. Z is a function of x and y. In other words, there's no top layer, bottom layer. It's like vertically simple. You know what I'm saying? And do you remember what that ds was in surface area? ds looked like this. 1 plus partial x partial, what am I doing? Partial z partial x squared plus partial z partial y squared, like that, right? And then dx dy, our extension from the arc length function, right? Now, what is the difference? Difference is our function now, vector function, is a two-variable function which generally looks like this. Some kind of x as a two-variable function uv with I vector, and y as a function of uv with a j vector, and then z and function of uv with a k vector. Now the big difference is, as you saw yesterday, this thing could have some kind of macaroni, right? This thing does not have to be a function of z, so there's a top and a bottom. So it gives us more freedom to work with, okay? And later when we do a surface integral, we have to use this version, even if it's just a parametric surface like this. So if I parameterize that simple surface, and then we did it yesterday with x and y, and we do it like this, x, I, and y, j, plus your f of x, y, your z, with a k, like that. Okay, and then we'll see, by redoing this, we'll learn how the procedure is, and it gives us exactly the same thing if the function is that simple, okay? So last time we did it, we drew these couple of little vectors, and we figured out what the vector n, vector a, and vector b is, right? And we took a cross product. And then we just came up with a vector like this, your vector a. I said if you vary x tiny bit in just that much in x direction, and then there's no change in y direction, and on the z direction it will vary according to the slope, and then times dx, right? And then we factored out dx, so it becomes 1, 0, this idea, right? Okay, now let's think about it. How can we, without thinking like that, we had to kind of geometrically get it, but how could we just using this format get from here to here? Do you notice that this vector is just the derivative of that thingy? Or that thingy with respect to x? You know what I'm saying? You know what I'm saying? So this thingy is in fact the partial r partial x dx, isn't it? You know what I'm saying? So we don't have to think with geometry. We can just take a partial derivative of this thing with respect to x, is the whole point here. And then likewise, then your b vector, and then remember we did it this way, no movement and just a little tiny movement in y direction, and then it'll move according to the slope in y direction, and then times dy, right? Then we factored out dy, so we have this thingy. But if you think about it, this is just the partial derivative of r with respect to y times dy now, isn't it? Oops, Good. Are we good? And as before, we take a cross product. So ds is equal to your A cross B, right? And that is equal to I, J, K here. And then your A vector, 1, 0, partial f, partial x, and then 0, 1, partial f, partial y, times dx dy. And if you do that, I vector, so this, right? Negative, partial f, partial x, I vector, and then j, negative vector, that one. So we have partial f, partial y, j vector, and then your k, just one. So we get this back. ds, this is a vector, by the way. And if you want just regular d, we are going to need this vector dx more eventually when we go to surface integral. But for now, your ds scalar is magnitude of that vector. So we have partial f, partial x squared plus partial f, partial y squared plus 1 dx dy. We get that thing back. Okay, now, well, then shall we verify this new tactic with one little thing? Do you remember spherical coordinate thingy? What we did yesterday? Yeah. So if we have a sphere, that's not how you spell sphere. Learn to spell. Sphere with radius r. Okay? That we did it like this. Just phi and theta, right? So we can have r sine phi cosine theta I vector plus r sine phi sine theta j vector plus r cosine phi k vector. This is how we did it. Now, so let's see if this thing still works, okay? Shall we find the partial derivative with phi? Okay. Then this thingy becomes r cosine phi cosine theta I vector, correct? And the next one, it becomes r cosine phi sine theta j vector, and this one turns into negative r sine phi k vector, right? So that's one partial derivative. The other partial derivative with respect to theta. So this thing turns into negative r sine phi sine theta I vector, and the next one turns into r sine phi cosine theta j vector, correct? And the last one dies, so 0k vector A. So my ds would be, can we imagine cross product, tiny little I, j, k here, and then we'll take cross product without rewriting the determinant? Yeah, that will be more convenient. So I always organize these things this way. So let's think I vector. This is 0 minus this, so we'll have r squared. Good. And then sine square phi cosine theta, right? Sine square phi cosine theta I vector. With me? Okay, j vector, j is the minus 1, negative 1. So this minus this, so r squared, right? And then this thing turns into positive because it's minus this, right? and we have negative, so this turns into positive. So we have r squared sine square phi and sine theta, j vector. You with me? And lastly, k vector, so plus k vector is this, which is r squared sine phi cosine phi sine phi cosine phi cosine square. This way r squared sine phi cosine phi sine square. Do you see that sine square cosine square gives you 1? So we'll have r squared sine phi cosine phi k vector. Good? Say yes. And not to forget this with d phi and d theta. I forgot to mention, but how do you know which one goes first? Because if you switch the order in the cross product, it gives you opposite. Right? You have to think about it. If it's just an umbrella looking type of surface, it doesn't matter because there are two sides. But if it's an enclosed surface, like which is sphere, then you want to do it in a way that you get outward ds vector. Okay? And then either you can think, okay, this way is phi and this way is theta, and think about it, or you just take a cross product. And then if you get something that is pointing inward, then you adjust it and then do it the other way next time. Okay? But convention is it's an outward pointing vector. Okay, and then I know from experience, if I do it d phi first and then d theta, then it gives me outward pointing vector. Do you see these are all positive vectors pointing outward? You know what I'm saying? Had I switched it, then everybody will be negative, and then that's not what I want. So you just switch it. You know what I'm saying? Okay, then we need this a lot in this form later, because we have to take a surface product with our vector field dotted with this thing. But for now, we want to verify if this thing gives us same answer as before, right? So let's do that. So do you see at least r squared and sine phi is common in all of them, right? So I'll take r squared and sine phi, and then I'll take gigantic square root, and let's see what's inside, what's left. That's the common factor part. And whatever's left, I need to square it to take a magnitude. So I have sine square phi cosine square theta. I'm basically taking a dot product of this vector by itself and putting it on the square root. Sine phi is out, so you have another sine square phi, and then here's a sine square theta. Good. And then plus this thing, sine is gone, so we have cosine square phi. I did not need square root that big. And the phi and the theta. You with me? Okay, let's think about this first one. Sine square is common factor, and cosine square plus sine square gives you just this now, right? Too much algebra? And then I have that cosine square. And then, of course, that's 1. And what do you know? This is your ds in spherical coordinate now, isn't it? Right. Remember your dv? What? Oh,
an r squared.
Of course, r squared. Right. In case this is a dv, then we had rho square and then d rho next to it, but without the rho, this was it now, wasn't it? And we have to get this with geometrically with looking at this little thing. You remember this thingy? And then calculating like that. Well, we didn't need any geometry. This scheme of partial derivative with respect to one variable. So let's review. If you take partial derivative with one variable, partial derivative with another variable, whichever your parameter is, uv, phi, theta, and then you cross the two, and that gives you ds. So that is the procedure here now, which gives us exactly something that we had before. But this ds factor is the one that is a lot more useful in the future. So I want you to keep that in mind. So we have to find the surface area of this cylinder, which is opening towards the y-axis. I'm gonna attempt to sketch this. I'm not sure how well it's going to go, but hey, let's try it. So we have cylinder. Let's change that color to black, blue. Okay, and this is sideways, right? Something like this. Okay, and that has to be inside our cylinder that is vertical. So imagine there is an axis like this. This y-axis and x-axis is sticking here. Okay, let's see how artistic I am, huh? So this cross section will look like. Is that even remotely imaginable? Something that is cut by, okay, no, not really. Okay, let's try it this way. I'm gonna throw this thingy right here. So that's the vertical cylinder that's going to cut this thingy, so maybe I'm not that artistic. Do you see it? This half, and then there's another half in the back. Can you see that? That's this cylinder cut out with a vertical cookie cutter? You want me to put it on new calc and forget this? Yeah, let's put it on new calc. Okay. It was a nice try, okay? Okay, so if we have a cylinder that is, we'll just make the radius 1. So we have x squared, my keyboard, x squared plus c squared is equal to 1. We have this cylinder, which is what I originally drew. And then I'm going to put vertical cylinder, which is x squared plus y squared is equal to 1. I forgot the plus sign there. There. What am I doing? I'm going to type. Okay. So whatever's inside this thingy, see, it can't see it because of this is blocking. That part is what I was trying to sketch, this thingy inside, you know, that thingy. Can you kind of get it? Actually, I'm not sure if I got that sketch right. No. My sketch was wrong. Let me go back here. So it's not this. So the cross section will be. How am I gonna sketch this? More like this, right? That top part that you see from the new calc, and then bottom part. Do you kind of see it, that top part, that if you cut this cylinder out with a cookie cutter, you know what I'm saying? I don't know how else to show it to you other than, that part right there. I'm gonna make the cylinder yellow so it's easier to see. That part is what we're trying to get. Okay, I'm gonna include this in the notes. I'm gonna put them right there. Okay, so anyway, this is the best I can do. If I shade it, is it a little bit better? That part, which is right there, that thingy. Okay. Alrighty, so let's parameterize this thingy, okay? We need some kind of a movement between independent of y, so x and z, right? So let's start right there. So this is a cylinder that I want to parameterize. So this is a cylinder that I want to parameterize. So R of UV. Okay, between x and z, we can have cosine and sine, correct? Are we remembering this from yesterday? So x is cosine as usual. So we can have a cosine u I vector, and then we'll worry about this j vector, and then plus a sine u k vector. This is between x and z. Are we good? What do you want to do with the y? Just take b. How about that? Because we really don't care what that is. Because it has an independent degree of freedom. You know why it has to be independent? Because it doesn't even enter the equation here. Do you get that? So this is x, which is a function of u. This is c, which is a function of u. And this is just y, which is a function of b. Good. Do you feel it? Okay, once you have that, then all we need is just take a derivative with respect to u and with respect to b and cross them. So it takes the thinking out of our, process. Okay, so let's just take a derivative partial with respect to u, which will be negative a sine u I vector plus 0 j vector plus a cosine u k vector. So far so good. And then we will take a derivative of this thing with respect to b. Then you will have 0 I vector plus 1 j vector plus 0 k vector. Good. So our ds is a cross product of these two. Good. So imagine ijk here with I 0. So you have just a cosine u, right? Negative, negative. So this is the magnitude of negative a cosine u, and this I vector, and then j, so is 0, so j is gone, and then k, that one is the only, so we have negative a sine u, and then du dv. So far so good. Okay, so magnitude of is this thing squared plus that thing squared and a square root, so you just get a du dv, eh? Oh, that's convenient, isn't it? Okay, then we're going to take a derivative, the integral, so your surface area is integral of just a du dv. Okay, that's nice, but what is our domain of this thing? U and V varies according to what, right? U varies, the way we set it up, I'm not sure if that can be figured out easily. This is looking from the top. So U varies that way, and then V, U is, U has to vary from 0 to 2 pi the way this thing is set up, correct? I'm not sure how I can vary Z, this part to that part,
What if you vary Z from negative A to A?
V from negative A to A, positive A?
Yeah, negative A to positive A.
Would that work? Let's think. Negative A to positive A. Would that give us a rectangular thingy? Let's sketch it and try to figure it out, shall we? I have a little reservation about this because why doesn't it turn into circle? Let me try that one more time. Okay, and then hold on. This is, let's say, looking at the top view. Okay, so this is X and Y. And then our cylinder is going towards the Y direction like this. So the way we have our U varied is that U is our circle. So it's our angle, isn't it? So the way we figure this thing out is this is U. U is between X and Z. No, that's not quite how I did it. Would that work? U has to vary from 0 to 2 pi from the way this thing is set up. I'm having a little problem of varying V. V is just going out. I think that'll work. V is just, so our domain is from YZ plane. So instead of this thing having XY, we want to have an XZ plane, and then U is this thing, angle, and then V is our radius. Do you see that kind of thinking? So looking at it from this side view, it does look like our polar coordinate. Good. And this is radius A. Okay, I think that'll work. So we'll have U varying from 0 to 2 pi. Somebody open up the answer key to check this. And then V from 0 to A. Okay. Does that just gives you 2 pi A squared, correct? Too much integrate. Somebody check the answer key and see if this is a correct answer.
I just checked the answer key and they got 8A squared. They did dy d theta, and their theta varied from 0 to pi over 2, and their y varied from 0 to A cosine theta.
But what is their answer?
8A squared.
8A squared, so we're off by a factor of 4. 8A squared, there's no pi in it?
No.
There's no pi?
Mm-mm.
There has to be a pi in it because this is circular. 8A squared, let me write down what you just said they have dx and dy?
They did dy d theta for
dy and d theta, and then y varies from
0 to a cosine theta.
a cosine theta, and then theta varies from
0 to pi over 2.
and don't they have some multiplying factor in?
Yeah, I guess that would be 8 because their integral
Yeah,
is that.
yeah, that kind of makes sense.
And then
And
a goes
in it like that, right?
Yeah.
I'm not sure if that makes sense. A cosine theta. So they are varying y from 0 to that circle. 0 to this. Oh, I see, I see, I see. I think I can make sense of it. Okay, okay. Because this was just kind of a wishful thinking. Okay, let's come back. And then I think I can do it in terms of u and v then. Okay. I'm gonna erase this. Let's just think like this. So we are looking at this from the side view. That means this is x and this way. We are looking at it from the top view. So this is x and y. Okay. So the way we set this up, our u is still an angle, isn't it? And u is still an angle that starts from x-axis and then goes into positive. So it's x, let's write x here so it's less confusing. U starts off from here and go off. But our other variable, that y, our v, their y, see y is the v according to answer key. So that varies still vertically this way. You know what I'm saying? That's our v direction. Good. Which means our v has to start from down here and end up there. Correct? So we have to figure out what that is. Well, this is the equation of the circle, isn't it? So do you see that this is cosine theta, right? Let me throw it. Okay, v is over here, this, and then our angle is u. Why is it cosine theta? Why is it cosine theta instead of sine theta? From here to here, so 0 to, it sure looks like sine theta to me. Okay, we'll try it and then see if that works out or not. So I want to integrate first in terms of v, and 0 to sine theta. Oh, I'm gonna pick up a negative sign. I have a bad feeling about this one, but we'll reverse engineer it, okay? And then I need to at least double it from here to here, right? And then this thingy is just 0 to pi over 2. So first quadrant, so I have 1, 2, 3, 4. And y varies from, because the other two comes from, there's a top one and there's a bottom one on the other side, right? So if I quadruple it, 4, and then there are 2 pairs, so that gives you 8. So that makes sense. And then the u, and my u will vary from 0 to pi over 2. Okay, and let's try this and see if this will work out or not. So 8, 0 to pi over 2, and then v is just av, right? av from 0 to sine theta du, and that would be 8 and 0 to pi over 2 of a sine theta, or sine u in our case. Du. Okay. Eight here. This is negative cosine. Oh yeah, it's gonna work out. It's a different setup. And that's where you see, I don't want to delete this just yet. If you plug in pi over 2, you get 0, and if you plug in 0 minus, that becomes a, am I missing a? You said 8a squared, correct?
I think you're missing a on the sine u, the very top.
Sine, oh, this has to be a, right? Yeah, this needs to be a right there. This radius is a, so this b will vary from 0 to a sine u, like that. Okay? Okay, so this works out perfectly. So this is a square, and this is a square, and then a square. How about that? So the reason that they have cosine here is they must have given here sine to x and cosine to z. You know what I'm saying? So it's just a different setup, but it worked out beautifully. How about that? Now I can delete this. Good. Okay, now let's look at this problem then. Okay, this one, I do have a picture saved. Let me get it from the Dropbox note, so I don't have to try to sketch it. Let me paste it right there. Just thinking that's the picture. Okay, so we have a sphere, and we are taking this vertical cookie cutter and cutting it. Good. So this one is a little more straightforward to set up. Okay, so let's do that. Here, why don't we use standard spherical coordinate? Because this is a sphere with a radius a, isn't it? Okay, whenever you use the spherical coordinate, I tend to put this with a capital R. And then we are going to use phi and theta. And the reason for this is because if I use lowercase r, then r appears a lot in polar coordinate and spherical coordinate, and that's kind of confusing. So I just say capital R, okay? And that will be your a, and then this is sine phi and cosine theta I vector, correct? Our standard spherical coordinate. And plus a, and we have sine phi and sine theta j vector, and then lastly we have a cosine phi k vector. How about that? Okay, and experience tells me that I have to go with phi first, although in this case it shouldn't matter. I might get the opposite. Actually, we are taking a magnitude, so it should not matter, but it's a general experience thing. If I want ds vector, that thing to point outward, so it's my habit to always go with phi first. Okay, this thingy is then A cosine phi cosine theta I vector plus A cosine phi sine theta j vector, and this turns into negative A cosine, sine phi k vector. So far so good. Now partial with respect to theta. Okay, let's do that one, and that will be negative A sine phi cosine theta I vector plus A sine phi here cosine theta j vector, and this one dies plus 0 k vector. Good. Okay, so ds is the magnitude of cross product of this. So let's try to figure it out. So imagining I, j, k here, so I is this and this. So minus this, so you have a squared sine squared phi. So we have a squared sine squared phi and cosine theta. Good. And j vector, this, so we have that's 0, and this way is a squared sine squared, right? And this is a negative one, so this thing becomes positive. So a squared sine squared phi and then cosine theta. So far so good. And k vector, so this way, so we have that thingy minus this thingy, so it looks like we have a sine phi cosine squared plus a sine phi a squared sine phi cosine phi. What? Okay, hold on. This is cosine square and this is sine cosine, huh? Okay, it's more complicated than I wished, but let's just do it. So this way is a square sine phi cosine square sine phi cosine phi. I'm going to write this down at the bottom because I'm going to run out of space. Let's put it here. Sine phi cosine phi and cosine squared. Okay, plus, minus, and then we have this one, so make that plus now, and then a squared. We have sine phi cosine theta cosine theta. Did I screw up one of the derivative? This is cosine, sine, and this is sine. Yeah, I screwed this up. See, I'm taking a derivative with respect to theta, so this should have been sine, right? I knew it, because that looks a little weird. This should be sine, and the other one, yeah, I did the other one correctly. Okay, so let's look at that one again. So a squared sine phi cosine phi sine squared. A squared sine phi cosine phi and then sine squared theta. That and then the phi, the theta. So far so good? Okay, let's see what we got. You're breaking up?
The second term should be a squared sine phi, sine squared phi sine theta now, because you fixed
sine squared theta. Yeah, I wrote that.
The second term.
Oh, this term. Yeah, let's figure that one out again. That was a J one, right? So sine square phi sine theta. This should be sine theta. Yeah, nice catch. like that. Good. Are we all good now? Okay, let's see what we got. This a squared sine phi cosine phi is a common factor, and sine squared cosine squared gives you 1. So this whole thing is just that much. Good. A squared sine phi cosine phi is all we got. And I have sine squared phi and I have sine squared phi. So why don't I factor out a sine phi outside and try to figure out the magnitude of what is left. Good. So I will have gigantic square root of a square is gone and sine square. Oh, I cannot factor out sine square yet. Dang it. Hold on. I just factor out sine a and then I'll have to just deal with everything else. Good. Okay. So between these two, I have sine square phi. Oh, I have sine to the fourth power because I'm squaring everything and adding it up. And then I will have cosine squared theta plus sine squared theta. Good, between the first two, which is going to turn out to be nicely sine to the fourth power here. And between these two, I already have these two thingies, so I'll have just plus sine squared phi and then cosine squared phi. You with me? Okay. Then this is just sine to the fourth power. So now sine squared is a common factor, so factor that out. So we'll have, just leave it in. Let me see. So I'll have sine squared phi here, and then what's left here is sine squared phi and plus cosine squared phi, which is beautiful. And that becomes 1, so take a square root, so we just have a sine phi and then the phi, the theta. How about that?
I think you're missing a square on the A, because it turns into...
Missing a square on way, oh, a square, right?
Square.
Like that. A should be squared, because I have a common factor a square, I factor that out. Okay, so this is my ds. Now all I have to do is then integrate this, right? Let's study the region, because it's not really centered. This cylinder right here is not really centered at the origin, right? So I have to figure that one out in order to, just like in this case, we had to figure out this, the limits of integration, right? So let's do that. But we know that it's a cylinder, so it's circular. So I'm gonna sketch that thingy. Let's do it with this one. So we have that thingy, and our axis should run through about there. This thing never works out for me. Like that. Do you see that? This cylinder is touching, and then this radius is a over 2. Do you see it? This is a right here. Too much algebra? Or does anybody want me to explain what's going on? Okay, well then, let's go. So my surface area is, putting that thingy in, a squared sine phi, the phi, and the theta. And then we should totally go polar, right? Okay, so let's just think about this thingy. R r sine. Why am I still being confused about this? R cos this thingy, if I have to write down the equation of this thingy, this function right here. So this is R is equal to A cosine theta. Good? So far so good? Now I have to find the relation, because I cannot just create another variable. This is between phi and theta. And phi is not shown in this picture. This is theta, isn't it? Good, so I cannot just say, oh, phi, right? Then I have to find the relationship between these things. So let's see, what is R when we are doing spherical coordinate? I think R was rho sine phi, correct? Do you remember that relationship that our R used to be rho sine phi? Now this R then is therefore A sine phi now, isn't it? Because we are not varying rho, that radius of the sphere has been fixed, is equal to A cosine theta is what we have. So far, so good. Okay, now I want to find the, I'm going to erase this thing. I'm going to find the relationship. I'm going to write it in. So our here R is equal to A sine phi for the future generations. I have to find the relationship between phi and theta. Yikes. So we can say sine phi, and then I want this to be in terms of sine. You guys remember cofunction identity? That's been a while. How many years has it been since you did trig identities? Do you remember that one? So our phi here now is pi over 2 minus theta. That makes sense to you? I know it's not an easy thing to swallow. This limits of integration is the tough thing in this business, eh? Okay, so now we want to vary this thingy from 0 to whatever. I mean, our phi should vary from 0 to that thingy, our theta value. So 0 to, I'm going to zoom in, pi over 2 minus theta. Good. And our theta, let's just vary it from here to here and not to pi because there are two loops in it. So 0 to pi over 2, then we'll have to figure out the factor. What do we multiply this by? Well, at least there are two here, correct? This piece and this piece. But then just like before, there's a top piece and the bottom piece, correct? So there are two of them there as well. So we are multiplying this by 4. I think this will work out. Good? Say yes. Any questions? Okay, then integration itself is easy. Taking a squared out. So 0 to pi over 2. And this thing is negative cosine phi. And from 0 to pi over 2 minus theta. The theta like that, eh? Okay. Continuing, that is equal to 4a squared. 0 to pi over 2 now. And if I substitute pi over 2, that's cosine pi over 2 theta. Is that just sine theta? Say yes. Is it negative sine theta Or you want me to write that in 2 steps? I'll write it in 2 steps for the future generations. Substitute that in, so we have pi over 2 minus theta, and then minus turns into plus, and cosine 0 is 1. So far with me? And then use a co-function identity again, so maybe possibly there's a better way to do this. So this thing becomes now negative cosine theta plus 1. The theta like that. Good? Wait. I'm dumb. I had a cosine to begin with, so this was cosine. Then this is sine. Good. Now we can integrate, so we have 4a squared, and this thingy now turns back into cosine theta and plus theta. Good. Wow, long last. 4a squared, this is 0, pi over 2, so we have pi over 2 minus, substitute 0, and that's 1, and this is 0. Whoa! That turned out to be a lot more complicated than I wanted to be.